Okay, starting Unit 4, we're going to combine two lessons into one, 4.1 and 4.2. 4.1 is titled Exponential Functions. From that, we just need to talk about how to graph exponential functions. From 4.2, the title of that is called the natural number. And from that section, really all we need to get to is what's called continuously compounding interest. Both of these are topics that were covered last year in Algebra 2. So hopefully you'll remember a little bit of this. So let's start with 4.1. What is an exponential function? As opposed to other types of functions that we've learned about thus far. We've learned about polynomial functions, we've learned about rational functions. So, quick little background. You can keep track of some things we've learned about. So our polynomial function, that looks, something like p of x equals 3x to the 4th plus 2x to the 3rd minus 8x plus 2. Polynomial function, their graphs are smooth and continuous. There's no gaps, no interruptions in the graph, no asymptotes. Domain is all real numbers. We've learned about rational functions. That could be something like r of x is equal to 1 over x minus 2. A rational function is a function in the form of a fraction. These graphs do have vertical and horizontal asymptotes. So the graph of this might look something like this. We've talked about other types of functions. There's absolute value functions that have a V-shaped graph. So what makes a function exponential? The key characteristic of an exponential function is where is the variable. If you look at a polynomial function, the variable is always part of the base. Like here we have 3x to the 4th. The exponent is an actual integer. The variable is the base. And that's the key difference for exponential function. Exponential functions are of the form f of x equals a to the power of x. So we really need to remember here the difference between exponential functions and any other function is in an exponential function the unknown or the variable is the exponent. The base remains constant. Okay? So there are two types of exponential functions that we'll see, and it'll become more clear when we start graphing these. But the two types, one of them is exponential growth. If your base A is larger than 1. You also have something called exponential decay, and that's if your base A is less than 1 but greater than 0. Okay? From this, if you haven't noticed yet, A cannot be negative. Your base cannot be negative. That doesn't mean it can't have a negative coefficient in front, but the actual base itself must be positive. Okay? Now it can be larger than 1, an integer value. Larger than 1 could be some kind of a fraction value between 0 and 1. That determines the shape of the graph, but regardless of the base, as long as it's greater than 0, it's an exponential function if the variable is an exponent. Okay. Really all we need to do in 4.1 is graph exponential functions. So let's take a look at example 1. Since we're not exactly sure, now you might remember from last year what they look like, but I'm just going to assume that you don't remember. If you're never sure what a graph looks like, you can always graph by plotting points. So for part A, we're going to use the function f of x equals 2 to the x. We're going to see what that graph looks like. Now, why is this exponential? Well, the variable is an exponent. If we take a look at the base is larger than 1, so that means this is going to be an exponential growth function, which has a different looking graph than exponential decay. So first thing we do if we plot points is we have to have some points to plot. So making your XY table. And I'm going to start with 0 down here. Normally you start with 0 and then 1 and then 2. I'm going to start with 0 here. If x is 0, then we have 2 to the power of 0. And in case you forgot, anything raised to a power of 0 is equal to 1. So the point 0, 1 is on the graph. If we let x equal 1, then we have 2 to the 1 power, which is 2. So 2, 2 is on the graph. If we let x equal 2, 2 squared is 4. If we let x equal 3, 2 to the 3rd power is 8. So there are a few points for positive values of x and when x equals 0. So let's plot those. And 0, 1, 1, 2, 2, 4, 3, 8. So far we have that kind of a shape. Now what happens on the left side of the y-axis here? That's when x takes on negative values. So if x is negative 1, this is where you really need to recall your properties of exponents. If actually I'm going to move this down here so I have more room. If x is negative 1, then what we have is 2 to the negative 1 power. Negative exponents do not produce negative numbers. 2 to the negative 1 is the same as 1 over 2 to the positive 1, which is 1/2. So when x is negative 1, y has a value of positive 1/2, which is right there. If x is negative 2, then what we have is 2 to the negative 2 power, which is not negative 4. 2 to the negative 2 is the same as 1 over 2 squared, which is 1/4. So when x is negative 2, we're at 1/4, which is about right there. What you need to start thinking of is what happens as x gets sufficiently small in the negative direction. What happens to the y values? Well, the y values just get closer and closer to the x-axis without ever actually touching the x-axis or crossing through the x-axis. So this part of the graph gets closer and closer to the x-axis as x approaches negative infinity. And we've seen this type of behavior before when a graph approaches some kind of a barrier and then kind of levels off and follows that line. That's called an asymptote. So that's the graph of f of x equals 2 to the x. We found that by plotting a couple of points. This is considered exponential growth because as x is increasing towards positive infinity, y is increasing towards positive infinity. Now let's compare that to f of x equals 1/2 to the power of x. Same method, we're going to graph this by plotting points. So if we're making a table of values, if x is 0, then we have 1/2 to the 0 power, but anything to the 0 power is equal to 1. So it's 0, 1 is on this graph. Now if we let x equal 1, then we have 1/2 to the first power, which is 1/2. Right there. If x equals 2, then we have 1/2 squared, which means 1/2 times 1/2, that's 1/4. So we have 2 comma 1/4, which is right there. Now as x gets larger and larger and larger, all we're going to end up getting is smaller and smaller fractions. These fractions are never going to go negative, they're just going to get smaller and smaller, heading towards 0. So this part of the graph kind of skims along the x-axis as x approaches infinity. Now on the other side of the y-axis, when x takes on negative values, -1 for example, 1/2 to the negative first power. What we're trying to figure out here is what's 1/2 to the negative first power? Well, when you have a fraction that's raised to a negative exponent, what you can do is invert the fraction or make the fraction into its reciprocal. So that's going to be 2/1, and then you can use a positive exponent. Those two things mean the same thing. So 1/2 to the -1 is the same as 2/1 to the first power, which is 2. So when x equals -1, y is 2. If x equals -2, then what we have is 1/2 to the -2 power, which is the same as 2/1 squared. So that's 4. So this kind of graph looks like that. This is an example of exponential decay because as x is increasing, y is actually decreasing, getting smaller, exponential decay. And you can either tell that from the graph, from the shape of the graph, or you can simply look at the equation. It's exponential because the variable is an exponent and the base is less than 1 greater than 0. Now one more I want to take a look at. F of x equals -3 to the x. Now, it is exponential because the variable is an exponent, but we got to be careful what we consider the base. Okay? What is being raised to the power of x? Is it 3 or is it -3? So, if the -3 were in parentheses like this, then the -3 would be raised to the x power, but that would not make this an exponential function. Exponential functions have to have a positive base. So it's just 3 that's being raised to the power of x. This negative is a coefficient. It's really -1 times 3 to the x. So what effect does that negative sign have on the graph, and what type of exponential function is this? Is it growth or decay? Well, the base is 3, which is larger than 1, so it is growth. What effect does that minus sign have on it? Now, you've seen this before. If I ask you to graph y equals x squared, and then I ask you to graph y equals -x squared, then the minus sign up front is just a vertical reflection over the x-axis. Okay, and that's the same with any function. It could be y equals absolute value of x, and then y equals negative absolute value of x. That minus sign out in front of the function is just a vertical reflection. So what we're going to have is an exponential growth function. If we were to draw a rough sketch of this, it would be an exponential growth, but then it has to be reflected over the x-axis. It's going to look like this when we're done. So, got to be a little more accurate here, making a list of values. Now, if x is 0, then 3 to the 0 power is 1, but then you have to multiply by that negative sign, so it's -1. If x is 1, 3 to the first power is 3, but then you multiply it by that negative, and it's -3. and so on. If x is 2, 3 squared is 9, multiplied by the negative makes negative 9. So far we have these couple of points. Like that. If we take on negative values for x, 3 to the negative 1, this is what we have. We have negative, and then we have 3 to the negative 1. 3 to the negative 1 is just 1/3, so this is the same as negative 1/3. So when x is negative 1, we're at negative 1/3. These values are just going to get increasingly closer to the x-axis. Now actually what I should have been doing, I apologize, I forgot about this, we should have been talking about domain and range for each of these. So let's go back up to example 1, part A. Domain. Another definition of domain is the set of all possible inputs. So that means what numbers can x be? Well, you've seen from our table of values, x can be positive numbers, x can be negative numbers, x can be anything. We can take 2 and raise it to any power we want. So the domain is all real numbers. The range are what are the y values. Where if you take a look along the y-axis, there are no values of the graph that are less than 0 on the y-axis. But the graph never actually reaches 0 either. So the range is parentheses 0 to infinity. We don't include infinity because you never are going to get a y value of 0 in the y column. For part B, domain is the same. Negative infinity to infinity. Range is also the same. Parentheses 0 to infinity. Now part C, domain is the same. Domain is going to be the same for any exponential function. All exponential functions have a domain of negative infinity to infinity. Range on this one's a little bit different because this graph is pointing upside down. The smallest value that y is going to have is negative infinity. Okay. Up to 0. Now the graph approaches and it gets pretty dang close to 0. It gets as close as we can get to 0 without actually equaling 0. That's why we don't include 0. We have it as a parenthesis. Now this method of graphing exponential functions by plotting points, it works. It takes a little bit of time. You got to plot a few points. It's meant to be done a little bit differently. Here's a little bit shorter way of doing this. Example 2. You notice a couple of characteristics of these exponential functions. Each of them approached a horizontal asymptote. In each of the cases, part A, part B, and part C, the horizontal asymptote was the x-axis. So if we were to, let me do a different color here, if we were to draw a dotted line along the x-axis on each of the examples, example 1, part C, that's the horizontal asymptote here, and part B, it's the x-axis. And part C, it's the x-axis. Not always the case, but all exponential functions will have a horizontal asymptote. Other thing that these graphs have is a Y-intercept. Now let's choose one here. If we go back up to example 1a, if I were to put a -2, for example, here outside of the function, what effect would that have had on the graph? It moves the graph. Does it move it up, down? Does it move it left or right? Well, depends on whether it's inside or outside the function. The -2 here is considered to be outside of the function. Anything occurring outside of a function is a vertical shift. Since it's -2, that would have moved the entire graph down 2 units, the entire graph including the asymptote. So the only reason on part A that the horizontal asymptote was at 0 is because there was nothing here. Another way of saying nothing is 0. I could have very well put a +0 and it wouldn't have changed the equation nor the graph. What I'm getting at is where is that horizontal asymptote going to be located? Well, it depends on what the number is here outside of the function. So that's actually what I'm going to have you do first when you're graphing these, is locate the horizontal asymptote. That's located by using transformations outside of the function. Okay. How do you find a y-intercept? Well, if you take a look at this point where my pencil is pointing, the x value is 0. It's going to be true of any y-intercept. So to find the y-intercept, we let x equal 0. So for example 2, we're going to graph not by plotting points, but by using transformations. Graph by using transformations. So what I want you to do for step 1 is locate the horizontal asymptote. Step 2 is find the y-intercept. And then step 3 is plot 2 more points. Any 2 points you want, doesn't matter. So you're going to have a total of 3 points, y-intercept plus 2 points, and then you're going to have the horizontal asymptote. It is going to be a little bit quicker to graph it this way. So if I want you to graph f of x is equal to 2 to the x plus 1, okay, this is essentially the same graph that we graphed in example 1 part A, 2 to the x. The only difference is this plus 1 is going to move the graph up 1 unit. So start by using that vertical transformation. Draw a graph. Okay. Rather than having your horizontal asymptote located along the x-axis, this plus 1 moves the graph and the asymptote up 1 unit. So next thing I want you to do is draw your horizontal asymptote up 1 unit. Okay, after you've done that, make your table of values with 3 points. One of those points is the y-intercept, and another 2 points if you're choosing. So to find the y-intercept, you let x equal 0. 2 to the 0 power is 1. 1 plus 1 is 2. So 0, comma 2 is your y-intercept. You know, whatever other points you want to do is up to you. I'm going to let x equal 1. 2 to the first power is 2 plus 1 is 3. So we have 1, comma 3. You want to let x equal 2. 2 squared is 4 plus 1 is 5. Now that you have the horizontal asymptote, you know the graph, as x approaches negative infinity, the graph is essentially going to follow the behavior of this horizontal asymptote. So that's what the graph is going to look like. I require 3 points. One of them has to be the y-intercept. You have to have the horizontal asymptote on there. 2 other points. Domain, like any exponential function, negative infinity to infinity. The range is parenthesis. The smallest number that the y values are going to take on, the smallest number they approach is 1. They're never going to actually equal 1 because that's where the asymptote is. So it's parenthesis 1 to infinity. Okay, and this method could work, if we make this part A, this method could work for exponential decay functions. If we have f of x is equal to 1/3 to the power of x minus 2, then same 3 steps. Locate the horizontal asymptote. This right here, minus 2, is going to move the horizontal asymptote down 2 units. Okay, now you make a table of values with 3 points. One of those, x has to be 0. 1/3 to the 0 power is 1. 1 minus 2 is negative 1. Now, it doesn't really matter what values you choose for x. Some values, especially when the base is a fraction, some values might be a little bit better than others. Here's what I mean. If you let x equal 1, 1/3 to the first power is 1/3, but then you have to take 1/3 and subtract 2 from that by hand. I would rather not do that by hand. I'm going to what I would recommend when you have a base that's a fraction is to actually use negative values for your exponent. Why? Well, 1/3 to the negative 1 is the same as 3 over 1 to the first power, which is 3. 3 minus 2 is 1. So negative 1, comma 1 is on the graph. Same thing here if x equals negative 2. 1/3 to negative 2 is the same as 3 over 1 squared, which is 9, and then you subtract 2 from that and get 7. So negative 2, comma 7 is on the graph. Okay, domain. It's all real numbers. Range. Is negative 2 to infinity. Now we've talked about vertical transformations up and down. What happens if I had put maybe a +1 there next to the x? That's considered to be inside the function. If it's inside the function, that's going to move the graph left or right. But if a graph is moving to the left or to the right, that does not affect the location of the vertical asymptote. So let's just do one more example here. Let's see what happens when we start messing around with values and transformations inside the exponent there. So example 3. Same thing, we're going to graph. So 2 to the x plus 1 power minus 1. So first thing we're going to do is, first thing we did in the other two is locate the horizontal asymptote. This minus 1 means the graph and the asymptote have moved down 1 unit to negative 1. So now when x equals 0, you plug a 0 in for this x and then you add 1 to it first. 0 plus 1 is 1. 2 to the first power is 2. 2 minus 1 is 1. So 0, comma 1 is on the graph. If x equals 1, 1 plus 1 is 2. 2 squared is 4. 4 minus 1 is 3. I'm actually going to let x equal negative 1 here because negative 1 plus 1 is 0. 2 to the 0 power is 1. 1 minus 1 is 0. So negative 1, comma 0. So the graph looks like that. That's really all that's been assigned from section 4.1. Unfortunately, it's not a lot of the material in 4.1, and the reason for that is most of what you would do in 4.1 requires a calculator. There's a lot more in 4.1 than this, but if we're limited to no calculators, this is about all we can do. Now 4.2 is titled The Natural Number. Also something that you were introduced to last year. The natural number is called the number E. If that sounds familiar to anybody. It's used in a lot of practical applications in mathematics and biology and chemistry, and it's actually a very, very, very common number to use, E. Now E is just a symbol that represents an irrational number, much like pi. Pi is 3.1415. The letter E is just a letter that represents an irrational number. And what we're going to see here in a second where that irrational number comes from. It's not just some number somebody made up. Like pi, 3.14 is not just some randomly generated number. If you take a circle and then measure its diameter and then measure its circumference, then pi is equal to the circumference of that circle divided by its diameter. No matter the size of the circle, large or small, any circle that you measure, its circumference divided by its diameter is always going to give you a value of 3.14, whatever it is, all the way out to this decimal never stops. That's where pi comes from. Now where does e come from? So this expression right here, 1 plus 1 over n to the power of n. What we're going to do is make a table of values. If this column is n and this column over here is this expression 1 plus 1 over n to the power of n. Now a lot of this would require a calculator, so I just want you to write this down. Don't bother using a calculator to figure out what this actually is. But if n equals 1, we have 1 divided by 1, which is 1. 1 plus 1 is 2. 2 to the first power is 2. Now if n equals 5, again you'd have to have a calculator for this, but if we increase the value of n to 5, we get a value of 2.4883 about. So n increased quite a bit. It went from 1 to 5, but this column didn't increase that much. It went from 2 to about 2.4. Now if we double n to 10, then this value increases only to 2.5937. Now if we get really drastic here and change this to 1,000, there's a huge jump in our n value. It went from 10 to 1,000. Surprisingly, that does not affect this column very much at all. This becomes 2.7169. Okay. If we make an even larger jump to 100,000. Now why is this column not increasing very much? Because if n is increasing, this is a very, very large exponent, but the problem is 1 divided by 1,000 or 1 divided by 100,000 is a very, very small decimal that we add to 1. So essentially the larger n gets inside the parenthesis, the larger n gets, the closer this value gets to 1. And when you take 1 and raise it to any power, it just remains 1. So that's why there's not a huge increase in these numbers as n gets larger. But if n is 100,000, we get 2.7182. 7. We go to the 1 million. We have 2.71827. Now, what happens as n approaches infinity? If we let n get so large that n has approached infinity, we went to 2 billion, then 5 trillion, and then all the way up as large as we could get, all the way to n approaches infinity. You can see that the growth here, 2.71827, now this decimal would go on. As n approaches infinity, then this expression 1 plus 1 over n to the nth power is 2.7182 ... Now it does change, but the change happens in the 1 billionth place or the 1 trillionth place. The changes in decimals occur way out here. And this is what we call E, 2.7182 ... Where does E come from? It comes from this expression as n has approached infinity. So when you think of E, it's approximated by the value 2.71, just like you would think of as pi is 3.14. Why the letter E? Well, the mathematician that really studied this quantity was Leonard Euler. His last name is Euler, E-U-L-E-R. So they just gave first letter E. This number is also called the Euler number sometimes, but more commonly it's referred to as the natural number. Well, what's so special about it? Well, the reason it's called the natural number is this quantity right here, 1 plus 1 over n to the power of n, surprisingly enough, can be used to describe a lot of naturally occurring phenomenon, like how money grows in a bank account, how populations grow in the wild, how bacteria grows. It's surprising and shocking how many things can be described using this quantity and this value 2.71. Now E is most often, almost exclusively, a matter of fact, is most often used as a base in exponential functions. So for example, function f of x equals e to the power of x. E is used as a base here of an exponential function. It's exponential because the variable is an exponent. What type of exponential function is this? Well, it depends on the base. E has a value of 2.71, which is greater than 1, so this would be considered exponential growth. Two things we need to do here in 4.2 real quick. Example 1, graph by using transformations. If I ask you to graph f of x equals e to the x plus 3, you're going to graph this using the same techniques we talked about in the last section, 4.1. So make a graph. The plus 3 moves the entire graph up 3 units, including the asymptote. So plot your asymptote. You need a couple of points. Now, some of these you aren't going to be able to find without a calculator, so do some here and just make your best estimate. If x is 0, for example, e to the 0 is the same as anything to the 0 power. It's 1. 1 plus 3 is 4, so 1, 4 is on the graph. The rest of these, unfortunately, would have to be done with a calculator. E to the first power is just e, which is about 2.71. 2.71 plus 3 is 5.71. That one I guess we could have done without a calculator. 1, and then 5.71. Let's say 1, 2, 3, 4, 5. 5.7 about right here. Yeah, but you'll see here e squared. That's 2.71 squared plus 3. That's pretty hard to do by hand. So with these ones in particular, I won't require 3 points. That graph looks something like that. What we're going to use a lot of, not necessarily in this particular section, but in 4.4 and 4.5 and even 4.6 of our textbook, is something called continuously compounding interest. When you deposit money into a bank account or when you borrow money at a certain interest rate, it's not, there's two types of interest. There's compound interest and there's simple interest. If I borrowed $100 from somebody and they said, all right, you just got to pay me back with 10% interest, then I would owe them $110 because 10% interest on $100 is $10. So that's simple interest. Now, if I borrowed $100 and somebody said, all right, you got to pay me back, but I'm going to charge you $10 or 10% interest per month. So if I don't pay within the first month, I owe them $110. If I don't pay them in the second month, it's 10% interest on $110. So you're not just adding $10 every month, because the principal balance is always increasing. So the second month, you'd have to take 10% of $110. That would be the interest added on. If I don't pay within the third month, it's 10% of the new growing balance. That's called compound interest. The interest is accrued over a period of time at regular intervals, and every time the interest is accrued, the balance that you have in the account or the balance that you owe, whatever it is, increases. Now, continuously compounding interest, there isn't a specific compounding interval. Like it's not going to compound per month, it's not going to compound per quarter or semi-annually. It's continuously compounding every moment of time. The formula for that, this may look familiar for some of you from last year. A is equal to P times E to the rate times time, where A is the future amount of the investment, P is the principal investment, that's what's initially put in, the principal investment. R is the interest rate, and T is time. So I only assigned one problem from 4.2, and we're going to see a lot more of this later on in 4.4, 4.5, and 4.6. So the one problem you have looks something like this. Example 2. How much money would you have if you invest $10,000 into an account yielding 6% interest compounded continuously Now we're going to just vary the time intervals. What if you left it in there for 5 years? What if you left it in there for 10 years? What if you left it in there for 30 years? So since this is compounding continuously, we're going to use that formula. A is equal to the principal times e to the rate times time. A is the future amount. That's what they're asking us to find. How much money would you have or will you have in the future if you invest $10,000? So this $10,000 is our principal investment into an account yielding 6% interest. Now you got to be careful. Interest or percents are not numbers you can use in formulas. The word percent means of 100. 6 of 100 means 6 divided by 100. That's 0.06. So 0.06 is the interest rate we're going to use. And part A and part B and part C, we just vary the amount of time that's left in there. So for part A, the future amount is equal to $10,000 times e to the 0.06 times 5. And all you're going to be able to do, since we don't have calculators, is leave it exactly like that. I know it sounds stupid because we can't actually find the value. And the way that we're going to use this later on in 4.4 and 4.5, we don't have to have a calculator for those. These, unfortunately, you do. I just wanted you to get used to knowing what the variables mean, the different interest rates and times. So for part A, you just leave it like that. That is the future amount, 10 times e to the 0.06 times 5. If we did have a calculator, you'd be able to find out what that actual value is. For part B, all you got to do is, alright, so the ending amount is your principal investment, $10,000 times e to the 0.06 times 10. And just leave it alone. You don't know how to solve that by hand or simplify it by hand, so don't worry about it. For part C, same investment, $10,000, but now it's times e to the 0.06 times 30. So I know it seems pretty stupid. Why the heck we learned about this if we don't really use it? What we're going to do later on, once we learn about logarithms, is I can ask you different variations of the same problem. For example, if you invested $10,000 and after 5 years it became $45,000, what was the interest rate? Or if $10,000 grew to $20,000 at 5% interest, how long did you leave it in there? So we'd be solving for different parts of this formula, which can be done without a calculator, but we have to know a little bit more about logarithms. So that's what's coming up later on in chapter 4. But for 4.1 and 4.2, that is about it.